You've heard the claim that everything in our galaxy orbits the black hole at the center, like there's one ultimate boss in the middle, and all the stars, including your sun, just march around it. It sounds strong, it sounds simple, and it's mostly wrong. Not because there isn't a black hole there is, called Sagittarius A star, sitting about 26,000 light-years away, with roughly 4.3 million times the mass of the sun. The problem is you don't actually orbit that thing in the way people say. And once you see why, the whole center of the galaxy idea starts to look a lot less obvious. But before we continue, please subscribe to the channel to give your support. Let's continue. Let's start by killing the viral version of the story. The meme line goes something like, everything, including you, orbits the supermassive black hole at the center of the Milky Way. It's shareable, it's dramatic, and it gives this very neat picture, one central monster, one big circle. But gravity does not care about being neat. The real galaxy is not just one black hole with some decorative stars stuck around it. Most of the mass is not in that black hole at all. Most of the mass is spread out in hundreds of billions of stars, clouds of gas and dust, and a huge halo of dark matter you can't see. So when you repeat that sentence, everything orbits the black hole, you are skipping over the main source of gravity in the system. So if you don't orbit Sagittarius A star directly, what do you orbit? Right now, in this second. The orbit that actually matters for you is the most local one. You are on Earth, and Earth orbits the Sun. The average distance is about 150 million kilometers, around 93 million miles, one astronomical unit. That loop takes 1 year, and that's the timescale your life is built around. Seasons, calendars, everything. The Sun's gravity is what keeps you from flying off into deep space. But this local orbit is not happening in a static background. While Earth goes around the Sun is moving too. The Sun is tearing around the inner part of the Milky Way at roughly 225 kilometers per second. We'll call it 225 kilometers per second to keep the numbers clean. That's about 810,000 kilometers per hour, around 500,000 miles per hour. For comparison, a low Earth orbit satellite does roughly 7.5 kilometers per second. A rifle bullet is around 1 kilometer per second, depending on the gun. Your star is cruising at well over 200 times that bullet speed, non-stop. At that speed, one full lap around the galactic center takes about 230 million years. One galactic year is longer than the time between the first dinosaurs and us. So when you talk about your orbit, it's not just Earth around the Sun. It's the whole solar system doing this enormous, slow 230 million year marathon around the inner galaxy. Now, here's the next logical question. If the Sun is going around the galactic center and there is a black hole near that center, doesn't that mean you're basically orbiting the black hole just from far away? This is where the details matter. Near the very center, inside roughly the inner light year, the black hole's gravity dominates. In that region, you can absolutely say that stars are orbiting Sagittarius A star itself. Astronomers have tracked individual stars there with names like S2 in infrared light. S2 moves on a stretched out ellipse going around once every 16 years. When it swings closest to the black hole, it reaches speeds of more than 7,600 kilometers per second, about 17 million miles per hour. That is a place where the black hole is the clear boss, no argument. But now jump back out to where the Sun is, roughly 26,000 light years away from the center. Here, the story is different. The pull you feel is not mainly from the 4.3 million solar masses in Sagittarius A star. The total mass inside the Sun's orbit is in the range of tens to hundreds of billions of solar masses. That mass comes from all the stars, all the gas, all the dust, and a giant amount of dark matter. The black hole is just a tiny fraction of that total. So the Sun's orbit is really around the combined center of mass of all that stuff, not around the black hole as a single object. If you somehow removed Sagittarius A star and left everything else the same, the Sun's orbit would barely change at all. So when people say the Sun orbits the black hole, they are compressing a complex situation into a simple picture. And in the process, they point your attention to the wrong piece. It's like describing the motion of a car by saying everything orbits the gas tank, just because the tank happens to sit near the middle. The center of the galaxy we talk about in astronomy is really the center of mass of the whole system, and the black hole just happens to sit very close to that. Close, but not perfectly fixed, not the single anchor of everything. This leads to the real question that should be bugging you now. If the black hole is not the true center that everything else orbits, then what is it doing? Is Sagittarius A star just sitting there, perfectly at rest in the middle of the Milky Way, or does it move as well, pulled around by the same gravity that moves the stars? If you could somehow freeze all the stars, gas, and dark matter in place, and then carefully trace the path of the black hole itself over billions of years, would you see a clean circle, or a wobble, or a drift? That's the puzzle that takes this from a cool space fact to a deeper, more uncomfortable idea. Because the moment you ask, what does Sagittarius A star orbit, you're really asking, what is the next level up in the gravitational hierarchy? And is there an end to that ladder? Does it orbit the Milky Way's center of mass? Does that center orbit something inside the local group of galaxies? Does the local group orbit something inside the larger supercluster structure? Or does the whole idea of orbiting something just stop making sense at some scale? By the end of this full story, you're going to have two key takeaways. First, that center of the galaxy is more like an accounting concept than a throne in space. And second, that at the largest scales, asking what does this object orbit eventually breaks down and forces you to think in terms of motion through an expanding universe, not neat closed loops. But before we can climb up that ladder and answer the big question, we need to lock down something basic: how we know Sagittarius A star is really there and that it is a black hole at all. If you're going to say this thing orbits that thing, you need hard numbers. You need the mass, you need the size, and you need the position, nailed down as precisely as possible. Here is the first key point. You do not see Sagittarius A star in normal visible light. It is buried behind clouds of dust and gas in the inner galaxy. What you see instead is what it does to the stars right next to it. Astronomers switch to infrared, which can pass through a lot of that dust, and they watch individual stars near the galactic center, year after year, decade after decade. These stars, with names like S2 and S29, do not drift slowly in straight lines. They loop around an invisible point on tight, clear paths. One of them, S29, comes in to about 13 billion kilometers from the center, roughly 90 times the distance between Earth and the Sun. And at closest approach, it's moving at about 8,740 kilometers per second, close to 19.5 million miles per hour. Speeds like that are not casual. At those speeds, the gravity yanking on that star has to be enormous. Otherwise, it would just fly off and never come back. So those stars act like test particles, like probes you didn't have to launch. You track their orbits, you record how long they take to go around, you measure how stretched out the paths are, and you plug that into the same basic physics that describes planets around the sun. The same logic that lets you weigh the sun using Earth's orbit lets you weigh whatever is sitting at the center of these stellar orbits. The twist is that here you also have to include general relativity, because the speeds and the depths of the gravitational well are high enough that Einstein's corrections matter. When you do that analysis over and over from independent teams, you keep getting the same answer. The thing at the focus has a mass of about 4.3 million suns. Now, mass by itself isn't enough. You also care about how concentrated that mass is. With these orbits, you can put an upper limit on the size of the central object. The stars get so close that you know all that 4.3 million solar masses must fit inside a volume smaller than our solar system, no more than a few light hours across. A light hour is the distance light travels in 1 hour, about 1 billion kilometers, around 600 million miles. So you're talking about millions of suns worth of mass squeezed into a region not much bigger than the orbit of Mercury. If you try to cram that much mass into a ball that small and keep it as normal matter, you run into a problem. The escape speed, the speed you'd need to get out, climbs up to a significant fraction of the speed of light. At that point, there is basically only one solution left in standard physics: a black hole. This is why people are confident calling Sagittarius A star a supermassive black hole and not, for example, a tight cluster of dark stars or some strange swarm of compact objects. If it were a bunch of smaller things instead of one black hole, the orbits of the nearby stars wouldn't stay so clean over decades, and the cluster itself would have to be packed so tightly that it would collapse. The clean, repeatable stellar loops are telling you, very plainly, you're dealing with a single deep gravitational well, not a loose group. That was the argument from motion. Then another line of evidence arrived from a totally different direction. In 2017, radio observatories all over Earth linked up to form one giant virtual telescope, the Event Horizon Telescope. By combining signals from dishes spread across the planet, they reached a resolution sharp enough to see structure on the scale of the black hole's own shadow at the galactic center. In 2022, they released the image. It's not a crisp sci-fi style picture, but it's enough. You see a bright, lopsided ring of radio emission with a dark patch in the middle, the shadow where light paths get swallowed. The diameter of that ring is around 51.8 million kilometers, roughly 32 million miles, about 37 times the diameter of the Sun. When you take the mass from the stellar orbits, the distance to the galactic center, and the equations of general relativity, you can predict what size shadow a black hole like that should cast. The observed ring size matches the prediction. A different kind of object wouldn't give you that combination of mass, size, and shadow. While all of that is going on, those same star orbits are doing something else for you. They're telling you exactly how far away the galactic center is. When you fit those orbits, you're working with angles on the sky and physical speeds. To get both to agree, you need to know the distance. The best current numbers put the center at around 26,000 to 27,000 light years away. That distance is not just a random trivia fact. It sets the scale for the entire Milky Way. If that number shifted by even 5%, every distance you have estimated using the center as a reference would have to be updated. The size of the disk, the positions of spiral arms, the orbits of many stars, the inferred mass of the dark matter halo, all of it would move. Now, you can see why this matters for the question we care about. When you ask, what does Sagittarius A star orbit, you're really asking, what is the exact center of mass of the Milky Way, and where is the black hole relative to that point? The stellar orbits and the Event Horizon Telescope pin down both the mass of the black hole and its position in three-dimensional space. They show you that it sits very close to the dynamical center, but it is not the whole story. Most of the galaxy's mass is not in that central point. It is spread out in the bulge, the disk, and the dark matter halo. The true gravitational center, the barycenter, is defined by all that mass, and Sagittarius A star is just one heavy piece in that system. So now that you have hard evidence that the black hole is real, that its mass is measured, and that its position is locked down, you can finally ask the next step without hand-waving. If this thing is not the ultimate center, what actually controls your own orbit around the galaxy? And how much of that pull comes from Sagittarius A star versus the rest of the Milky Way? Here's the part that really messes with the simple everything orbits the black hole story. The orbit you're actually on right now has almost nothing to do with the black hole itself. You're strapped to a star that's doing something much bigger, much faster, and much stranger than just circling one object in the middle. Start with the basic hard numbers. The Sun is moving around the center of the Milky Way at about 220 to 230 kilometers per second. Let's lock it to 225 kilometers per second to keep things clean. That's roughly 810,000 kilometers per hour, about 500,000 miles per hour. A typical low Earth orbit satellite does about 7.5 kilometers per second, so your star is moving nearly 30 times faster than that, and more than 200 times faster than a rifle bullet. You don't feel it because everything around you is moving with you, but the entire solar system is on this huge track around the inner galaxy. That track is not short. One full lap at that speed takes on the order of 230 million years. That means since the dinosaurs first showed up and vanished again, the Sun hasn't even completed 2 full orbits. Human history, all of it, is a tiny sliver of one galactic year. So when you say, I'm orbiting the Sun, that's correct, but it's only the first layer. Underneath that, you and the sun together are locked into this 230 million year marathon around the galactic center, a loop so long you will never see even 1% of it completed in the lifetime of our species. So now the obvious question kicks in. At that distance from the center, who is actually pulling harder on the sun, the supermassive black hole or everything else in the galaxy? At around 26,000 light years from the center, the answer is not even close. The black hole at 4.3 million solar masses is a rounding error compared to the total mass inside the sun's orbit. Add up all the stars in the bulge, all the stars in the inner disk, all the gas, all the dust, plus the dark matter we can't see but we can feel through its gravity, and you get something like 100 billion to a trillion solar masses. That's tens to hundreds of billions of suns worth of mass. Put those numbers side by side. 4.3 million solar masses in Sagittarius A star versus maybe a few hundred billion solar masses in the whole inner galaxy. The black hole is heavy, yes, but it's not the main term in the equation. What the sun really orbits is the combined gravitational field of all that mass, the global potential of the Milky Way. You're not glued to one monster in the middle. You're riding the gravity of the entire inner galaxy. If you could somehow delete the black hole and leave everything else unchanged, the sun's path would barely notice. That leads you straight into the next weird piece. The rotation of the galaxy itself does not behave the way a simple Newtonian disk would. If most of the mass were in the bright central region and the inner stars, you'd expect the outer stars to slow down as you go farther out, the way planets in the solar system do. Mercury whips around fast, Neptune crawls. But when astronomers measure the speeds of stars and gas clouds far outside the visible disk of the Milky Way, they don't see that slowdown. Out there, 30,000, 40,000, even 50,000 light years from the center, orbital speeds stay around 200 kilometers per second. The rotation curve of the galaxy is flat, not falling. That flat rotation curve is one of the key reasons dark matter went from a weird idea to a serious component in our models. The visible mass alone cannot generate the gravity needed to hold those fast outer orbits in place. Without an extended massive halo of unseen matter surrounding the galaxy, the outer stars should have drifted away over billions of years. No halo, no long-term stable orbits like the one the sun follows. So your real orbit is shaped not just by stars you can see in long exposure photos, but by a huge invisible halo of something we still don't fully understand. All of this still leaves a very human question hanging in your head. If gravity is always pulling inward, why don't we just fall straight into the center, into Sagittarius A star? The answer is that an orbit is just controlled falling with the right sideways speed. The sun is constantly falling toward the galactic center because of gravity, but it's also moving sideways at about 225 kilometers per second. In 1 second, it falls a tiny bit inward, but at the same time, it moves about 225 kilometers sideways, roughly 140 miles. That sideways motion means that by the time it would have hit the center is no longer straight ahead. It has slid to the side in the sun's frame. So the sun misses, and then it misses again, and again, over and over for hundreds of millions of years. If the sun were moving more slowly, it would not miss by so much. Its path would curve inward and it would gradually spiral toward the center. If it were moving faster, it could overcome the inward pull and drift outward to a larger orbit, or even escape. Right now, its speed is tuned by gravity itself to be in that balance point where it doesn't crash inward and it doesn't fly outward. That balance is why orbits exist at all, at any scale. Earth balances around the sun balances around the galactic center of mass. It's all the same rule, just scaled up. But this brings us to a subtle but crucial detail people usually skip when they say the sun orbits the center of the galaxy. What do we actually mean by center? In physics, the point that matters is the barycenter, the center of mass of everything in the system. For the Milky Way, that center of mass is defined by all the stars, gas, dust, dark matter, and yes, the black hole too. Sagittarius A star sits very close to that point because it's such a concentrated chunk of mass, but it does not define the barycenter by itself. If you could move enough mass around in the bulge and the halo, you could shift the true center of mass without changing the black hole at all. So when you say the sun orbits the galactic center, the precise version is the sun orbits a Milky Way's barycenter. Sagittarius A star happens to be parked near that gravitational balance point, but it's not welded there. It can move slightly, it can wobble, it can respond to tugs from the nuclear star cluster and the larger mass distribution. The black hole is not a nailed-down pivot. It's a participant in the same gravitational game as everything else. And that raises the next level of tension in this whole story. If your orbit is around the galaxy's center of mass, and the black hole is only one player in that field, then what about the black hole's own motion? Is Sagittarius A star perfectly still at the bottom of the potential well, or does it have its own small orbit, its own jitter inside the crowded core of the Milky Way? You'd probably expect a 4 million solar mass black hole to sit dead still at the center of the galaxy, like a pin driven through the middle of a spinning wheel. No wobble, no drift, just the absolute reference point everything else moves around. That feels clean, it feels symmetric, and it's wrong. Even Sagittarius A star with all that mass does not get to be perfectly still. It moves, just a little, and that small motion already tells you something important, that even the center of the galaxy is just another object inside a bigger gravitational system. Here's the basic problem. The very center of the Milky Way is not empty space with one black hole in it. It's crowded. There are millions of stars packed into the central few light years, plus gas, plus compact objects like neutron stars and smaller black holes. All of them pull on Sagittarius A star, all the time. No single star can shove it around much, but together, with random positions and random motions, they produce a constant pattern of tiny gravitational tugs. That means the black hole does not sit perfectly at some exact mathematical point. It jitters around it, not in big loops like the sun's 230 million year orbit, but in tiny, slow, random shifts. This kind of jitter even has a name. Astronomers call it gravitational Brownian motion. In the same way that a dust grain in water gets kicked around by the random hits of water molecules, a massive object in a dense star cluster gets nudged by the random pulls of nearby stars. The scale is tiny in distance. We're talking milliparsecs, a thousandth of a parsec, and 1 parsec is about 3.26 light years. So the black hole's wandering is on the order of thousandths of a light year, fractions of a trillion kilometers. But when the object doing that wandering is about 4.3 million times the mass of the sun, even a tiny shift is a real physical orbit in the local gravitational potential. Not noise you can just ignore. You might think, okay, but do we actually see this motion, or is it just a theory? Astronomers have a way to check. They use very long baseline interferometry, linking radio telescopes across continents to pinpoint the position of Sagittarius A star on the sky with ridiculous precision. Then they compare that position to distant quasars, active galaxies billions of light years away. For our purposes, those quasars are basically fixed background markers. When you do this over many years, you see Sagittarius A star move. Most of that apparent motion is just us. It's the Earth orbiting the Sun and the Sun orbiting the galaxy, dragging our whole observing platform along. But after you strip that away, there is a leftover drift, a residual proper motion of the black hole itself of a few kilometers per second relative to the Milky Way's center of mass. A few kilometers per second sounds tiny next to the sun's 225 kilometers per second around the galaxy. But remember what you're talking about here. A supermassive black hole that is supposed to be at the very bottom of the galaxy's well. The fact that you see any residual motion at all means that bottom is not a sharp point with the black hole glued to it. It's more like a shallow basin, and the black hole is rolling slightly around in it, reacting to the rest of the mass in the center. Again, the motion is small, but it is not zero, and not zero is the key for this whole question about what it orbits. Now you need to ask, what is the basin actually made of? In the inner few parsecs, that's the inner few light years, there is a dense nuclear star cluster. We're talking millions of stars inside a region that, on the sky, is a tiny dot. Their combined mass is big, comparable to or even larger than the mass of Sagittarius A star in that immediate volume. Add in the local dark matter and gas, and you get a gravitational potential that is not just black hole plus decoration. It's a combined system, with the black hole plus the star cluster plus dark matter all shaping each other's motion. So, in a strict dynamical sense, it's more accurate to say that Sagittarius A star moves inside the gravitational well of the nuclear star cluster and the inner dark matter distribution, not that everything else is simply orbiting a fixed black hole. When you talk about orbits at that scale, you're talking about the whole inner Milky Way with its own center of mass, and the black hole is one massive component moving in that shared potential. It dominates the gravity inside roughly the inner light year, so stars like S2 clearly orbit it. But step out to few parsecs, the balance shifts. The cluster and the halo matter start to count. This gives you the first solid technical answer to the big question. On the smallest meaningful scale, Sagittarius A star orbits very slightly around the barycenter, the center of mass, of the inner Milky Way, defined by stars plus gas plus dark matter in that central region. It is not the absolute anchor that everything else orbits. It is part of the mass budget that defines the anchor in the first place. The black hole pulls on the cluster pulls on the black hole, and the true center is the weighted average of all of it. But once you accept that even the central black hole is just another mass moving around the barycenter, you have to push the question one level up. If Sagittarius A star is orbiting the inner Milky Way center of mass, what is that entire inner region orbiting inside the full galaxy? And beyond that, what is the whole Milky Way actually moving in when you include the thing that really dominates the mass on galactic scales, the dark matter halo you never see, but you can't escape? You live in a galaxy where most of the mass is invisible, and yet that unseen stuff controls almost every orbit you care about, including your own. That's the first big correction you have to accept before you can say what Sagittarius A star really orbits. The black hole is not sitting in the middle of a neat, self-contained disk. The whole disk and the black hole are sitting inside something bigger and heavier. The stars you see in beautiful Milky Way photos, the spiral arms, the bright bulge in the center, all of that is just the visible part. If you only counted that, you'd get maybe a couple 100 billion suns worth of mass. But when astronomers measure how fast stars and gas clouds move at different distances from the center, the gravity they feel is way stronger than what that visible mass can explain. The best fit is that the Milky Way is wrapped in a roughly spherical halo of dark matter, reaching far beyond the visible disk, with a total mass around 1 to 2 trillion solar masses. That's 1,000 to 2,000 billion suns, give or take a factor of a few. So most of the galaxy's pull is coming from something you cannot see at all. This dark matter halo is not just some thin shell. It extends out to a few 100,000 light years from the center, way past the disk where most of the bright stars live. The sun, at about 26,000 light years from the center, is deep inside this halo, not near its edge. That means when you talk about your real orbit, you're not just orbiting the visible disk or the central bulge. You, the sun, Sagittarius A star, every star you know by name, are moving inside the gravitational field of this huge dark structure that outweighs everything else. And the halo itself is not perfectly smooth. There's evidence for dark matter subhalos, smaller clumps of dark matter orbiting inside the main halo. We see hints of them because they disturb thin streams of stars, the leftovers of smaller galaxies that the Milky Way has torn apart. A star stream that should be a clean, narrow line in the sky shows a kink or a gap, like it has been punched. Backtracking that disturbance tells you there's a clump of mass there with almost no visible stars. One such subhalo seems to weigh around 25 billion suns and sits only a couple of thousand light years away from us, basically in our wider neighborhood, and yet you don't see it directly. It's just gravity, no light. So now ask the key question. If you could somehow turn off the stars, gas, and dust, and leave only the dark matter, where would the Milky Way's true center of mass be? It would still be there. The dark halo is so massive that even without the bright disk, there would be a well-defined gravitational minimum, a point where the total pull balances in all directions. That is the deeper center your galaxy cares about. When you put the luminous disk, the bulge, and the black hole back in, they all settle into orbits inside that dark halo's potential well. Sagittarius A star sits very close to that minimum because it's a concentrated lump of ordinary matter at the middle of the bulge, but it is not the thing that defines the minimum. The halo plus the bulge plus the disk together define the barycenter, the center of mass, of the whole Milky Way system. In other words, the black hole is responding to the halo's gravity just as much as the halo is responding to the black hole. On galaxy-wide scales, the halo is the boss. The disk, the bulge, and the black hole are more like embedded components. So when people say Sagittarius A star is at the center of the galaxy, the precise version is more like the black hole happens to sit close to the peak density of normal matter in the galaxy, near the bottom of the combined gravitational well. It's a tracer of where the galaxy's potential well is deepest, not the fundamental anchor that everything else orbits. If the dark matter halo were different, shaped differently, more massive on one side, the location of the true barycenter could shift a bit without changing the black hole itself. That gives you a cleaner level 2 answer to the original question. On galactic scales, Sagittarius A star orbits within the Milky Way's dark matter halo, very close to the galaxy's center of mass. It's locked into that larger structure, moving along with the disk and bulge inside a trillion solar mass gravitational cage. But that's still not the end of the story, because the halo, the disk, the bulge, and the black hole together are not sitting still either. The entire Milky Way package is moving through space, pulled around by other galaxies near us. So the next step up the ladder is obvious now. If Sagittarius A star is tied into the dark matter halo of your Milky Way, what is that whole halo galaxy black hole system orbiting inside our local patch of the universe? And who is pulling harder on us out there? Our own galaxy or our nearest big neighbor? Right now, your entire galaxy is moving toward another giant galaxy, and at the same time, both of them are falling toward a point in space that sits between them. So on this scale, asking what does Sagittarius A star orbit on its own actually stops making sense. You have to talk about the whole Milky Way as one object in a bigger multi-galaxy system. Start with the basics. Your galaxy is not alone. It lives in a small gravitational club called the local group. At the top of that group, there are two main players, the Milky Way and the Andromeda galaxy. Both are big spiral galaxies with huge dark matter halos, hundreds of billions of stars, and central black holes. Around them, there are dozens of smaller dwarf galaxies, including the Large Magellanic Cloud and the Small Magellanic Cloud, which you can see from the southern hemisphere as faint fuzzy patches in the night sky. All of these systems are bound together by gravity. They are not being pulled apart by the expansion of the universe. They're stuck with each other for billions of years. The most dramatic relationship in this group is the Milky Way and Andromeda. Andromeda sits about 2.5 million light-years away, and the light you see from it tonight left before humans even existed. When astronomers measure its motion along our line of sight, they find that Andromeda is not drifting away like most galaxies. It's coming toward us at something like 100 to 120 kilometers per second, around 220,000 to 270,000 miles per hour. Early on, with less precise data, the simple picture was, okay, we're on a head-on collision, we'll merge in about 4 to 5 billion years, end of story. That made for great headlines, Milky Way and Andromeda to collide. But newer measurements from missions like Hubble and Gaia added more detail. They don't just measure the approach speed, they measure the sideways motion on the sky as well. When you combine that, the story gets more subtle. The two galaxies are still falling toward each other, but Andromeda has some sideways velocity. That means a clean, guaranteed merger is no longer a sure thing. The current best estimates put the chance of a direct, dramatic merger over the next 10 billion years maybe around 50%, not 100%. In other words, we're definitely interacting, but the exact future path is more of a complicated dance than a simple two trains on a track scenario. And the Milky Way doesn't just feel Andromeda. One of the key extra players here is the Large Magellanic Cloud, the LMC. On a picture, it looks like a small, irregular companion galaxy, about 160,000 light-years away from us. Small is misleading. The LMC contains tens of billions of solar masses and stars and dark matter. That's not as much as the Milky Way, but it is absolutely enough to tug on our dark matter halo in a noticeable way. Recent work suggests that the gravity of the LMC is actually shifting the Milky Way's halo, pulling it slightly in its direction and changing our galaxy's motion through the local group. So even on this scale, your galaxy is not some rigid block. Its center of mass moves in response to the mass of its satellites. On this local group scale, trying to separate what does Sagittarius A star orbit from what does the Milky Way orbit really falls apart. The black hole, the disk, the bulge, the halo, the LMC orbiting us, all of that is tied together. The thing that has a meaningful orbit now is the entire Milky Way plus halo plus black hole package. And that package is orbiting, or more precisely, moving around, the barycenter of the local group. That barycenter is the center of mass of all the big pieces, mostly the Milky Way and Andromeda, with a smaller but still important contribution from the LMC and other dwarf galaxies. It sits somewhere in the space between the Milky Way and Andromeda, not inside either galaxy. Both big galaxies are falling toward that common point and then overshooting and curving around it over billions of years. So your level 3 answer to the original question now looks like this. Sagittarius A star orbits the Milky Way's true center of mass. That Milky Way barycenter, together with its dark matter halo, orbits the local group barycenter defined by both the Milky Way and Andromeda and their satellites. The black hole's motion is now just a detail inside that larger group-scale orbit. It's layers of motion stacked on motion. But even this is not the top level. Because if the local group is a bound island of galaxies, that island itself is not just sitting quietly. On even larger scales, the whole local group is moving toward massive structures outside it, like the Virgo cluster and the region we call the Great Attractor. So the next question is obvious and more uncomfortable. If your galaxy and its central black hole are locked into this local group orbit, then what is the entire local group falling into? And at what point does the idea of a clean orbit finally break? Here's the next twist. Even the whole local group, all those galaxies bound together, is not just drifting gently in space. It's plunging toward bigger piles of mass on an even larger scale. So at this point, when you ask, what does Sagittarius A star orbit, you're really asking, what does our entire little island of galaxies fall toward? And the answer stops looking like a neat loop and starts looking like a one-way slide. On these scales, the main thing that matters is where the mass is. Our local group sits in a region of the universe that isn't uniform. There are areas with more galaxies, more dark matter, more total mass, and areas with less. The big nearby heavyweight is the Virgo cluster, a compact cluster of thousands of galaxies roughly 50 to 60 million light-years away from us. There's also a broader, overdense region we've historically called the Great Attractor, a direction in the sky where galaxy motions tell us there's a serious amount of mass pulling on everything nearby. So the local group, with the Milky Way and Andromeda at its core, is not at rest. It's sliding toward these mass concentrations at hundreds of kilometers per second. Astronomers can actually map this large-scale motion. They measure galaxy redshifts to see how fast galaxies are moving away with cosmic expansion. Then they look at the peculiar velocity, the extra motion on top of that expansion. When you do this for thousands of galaxies around us, you see patterns. Galaxies are not just randomly scattered and drifting. They form filaments, sheets, and nodes in what we call the cosmic web, and they move along these structures pulled toward regions of higher density. From those maps, one especially important structure pops out, the Laniakea Supercluster. This is not a bound object in the same sense as a galaxy, but it's a region about 500 million light-years across where galaxy motions all seem to converge into a common gravitational basin. You can think of it as our home catchment area in the universe, a zone where thousands of galaxies, including the Milky Way and Andromeda, stream along large-scale filaments toward roughly the same overdense region. In that context, our whole local group is just one small component of a much larger flow. You can quantify that motion. Relative to the cosmic microwave background, which we'll talk about next, the local group is moving at about 600 kilometers per second. That's around 2.2 million kilometers per hour, about 1.4 million miles per hour. At that speed, if you turn space into a racetrack the size of Earth's equator, you'd lap the planet in under a minute. That number is not some random curiosity. It's telling you how hard the nearby supercluster scale structures are pulling on our entire group. Here's where the language needs to change. On these scales, the idea of a clean, closed orbit around the single center stops working. In the solar system, you have one dominant mass, the Sun, and planets move on nearly elliptical paths around it. In the galaxy, you can still talk about approximate orbits around the galactic center of mass, because the mass distribution is roughly symmetric and stable over long times. But at the scale of superclusters and the cosmic web, there is no single static point everything circles. You have many concentrations of mass distributed over hundreds of millions of light years, and structures are moving more like a flow down a complicated gravitational landscape than like planets on tracks. So when you ask, what does the local group orbit, the most honest answer is, it doesn't orbit one thing in a tidy loop. It's being pulled in certain directions by the combined gravity of structures like Virgo, the Great Attractor region, and the overall Laniakea Basin. The local group is following a path through that landscape, but that path is not a simple ellipse, and it's not closed. The positions and masses of clusters evolve. Dark energy affects how everything spreads out over time, and the whole pattern is dynamic. Put this back in terms of Sagittarius A star. On this level, you can say Sagittarius A star is locked into the Milky Way. That Milky Way is locked into the local group, and the local group is part of a larger stream of galaxies inside Laniakea, falling toward deeper gravitational wells defined by supercluster scale structures. There is no single thing it orbits at the scale. There is only a direction of fall and a speed through a large-scale gravitational field. That gives you a solid level 4 version of the answer. Sagittarius A star orbits the Milky Way center of mass. That, in turn, moves around the local group barycenter with Andromeda and the other galaxies. And that entire system is streaming as one unit as part of the Laniakea Supercluster, heading toward regions of higher mass density. Beyond that, orbit is no longer a neat word. It's motion in a field, not circles around a throne. But this raises a new problem. If everything on these scales is just flowing, how do you even define a speed in any absolute sense? Speed compared to what? If there's no universal center for Sagittarius A star to orbit, is there at least the universal reference frame you can measure its motion against? That's where the cosmic microwave background comes in, and it changes the way you talk about motion again. So at this point, you've got layers of motion stacked on top of each other. Solar system around the galaxy, galaxy inside the local group flowing inside Laniakea. The natural question is, fast relative to what? If everything is moving, is there any honest way to say how fast the Sun, or Sagittarius A star, is actually going through the universe? There is a kind of universal speedometer, and it's not a place, it's a glow. Space is filled with the cosmic microwave background, the CMB, the leftover radiation from the early universe. It's almost perfectly uniform, the same in all directions, but not quite. When we map the CMB across the whole sky, we see a very simple pattern on top of the tiny random ripples. One side of the sky is slightly hotter, the opposite side is slightly colder. That hot-cold split is called a dipole, and it's not because that part of the universe is different, it's because we are moving through the CMB. The side we're moving toward looks a bit hotter, the side we're moving away from looks a bit colder, thanks to the Doppler effect. So if you want a kind of rest frame for the universe, you use the frame in which the CMB looks perfectly the same in all directions. In that frame, you can define a real number for how fast are we going. So what does that number look like for the sun? When you measure the CMB dipole very carefully, you get a speed of about 370 kilometers per second for the sun relative to the CMB rest frame. That's roughly 1.3 million kilometers per hour, around 800,000 miles per hour. If you had a ship that could just lock onto that velocity relative to the CMB and fly in a straight line, you could cover the distance from Earth to the moon in about 20 minutes. That's the scale we're talking about. This isn't just the sun jogging around the galactic center. This is the sun's total motion through space-time when you pick the most natural 0 point the universe gives you. But that 370 kilometers per second is not one simple thing. It's the result of stacking motions from different levels. Part of it comes from the sun's orbit around the galactic center, about 220 to 230 kilometers per second. Part of it comes from the Milky Way and the local group being pulled by nearby large-scale structures on the order of 550 to 600 kilometers per second, relative to the CMB. And those contributions are not in the same direction. The sun's galactic orbit is almost opposite to the Milky Way's motion with respect to the CMB. So when you add them as real vectors in 3 dimensions, the numbers partially cancel in some directions and add in others. The final result is that net 370 kilometers per second. So the speed you quote versus the universe is a combined effect of local orbital motion and large-scale flow. Now take that idea and apply it back to the thing we care about, Sagittarius A star. In the CMB rest frame, what does it orbit? The honest answer is, it doesn't orbit the CMB at all. The CMB is not an object with mass that you circle. It's a radiation field that gives you a reference frame. In that frame, Sagittarius A star is basically sharing the same bulk motion as the rest of the Milky Way center, because it's gravitationally tied to the galaxy. Any small wobble it has relative to the Milky Way barycenter is tiny compared to the hundreds of kilometers per second of the whole galaxy's motion. So the statement you can make is, in the CMB frame, Sagittarius A star is moving at hundreds of kilometers per second through expanding spacetime, along with the Milky Way and the local group and the flow into Laniakea. This is where the language of orbit quietly starts to break. In the solar system, what does Earth orbit has a sharp answer: the sun, on a nearly closed path. In the galaxy, what does the sun orbit is a bit more subtle: the galactic center of mass inside a dark matter halo, still roughly closed. In the local group and the supercluster, motion is more like a flow than a loop. And in the CMB frame, you're not circling anything at all. You're just moving with a certain peculiar velocity, that's the technical term, through the overall expanding universe. Sagittarius A star becomes one more mass following that combined velocity, not a special object with its own separate orbit on these scales. So your level 5 version of the answer looks like this. When you measure things relative to the cosmic microwave background, you stop asking, what does Sagittarius A star orbit, and start asking, how fast and in what direction is it moving through spacetime? Its motion is just part of the Milky Way's net 3D velocity relative to the CMB. The black hole is no longer the center of anything. It's just a passenger in a much larger pattern of motion set by gravity and cosmic expansion. That raises the next, deeper question. If the CMB gives you a natural rest frame, does that mean there is actually a center of the universe that Sagittarius A star could orbit, some ultimate point everything is moving away from? Or is center of the universe itself the wrong idea, in the same way that what does it orbit is starting to be the wrong question on these scales? So after stacking all these layers of motion, it's natural to ask a sharp question. Is there somewhere a literal center of the universe that Sagittarius A star could orbit, the way Earth orbits the sun? The short answer is no. Not we haven't found it yet, but the idea itself doesn't match how the universe works on the largest scales. First key point, on very large scales, galaxies are not just flying apart through a fixed empty space. Space itself is stretching. That's what the Hubble-Lemma Trey law is really telling you. When we look at distant galaxies, their light is redshifted, and the farther they are away, the faster they appear to be receding. double the distance, roughly double the recession speed. That pattern is not what you'd expect from everything flying away from a single explosion point inside a normal, static void. It's what you get when the actual metric, the ruler we use to measure distances in space-time, is changing with time. The gap between galaxy clusters is increasing because the space in between is expanding, not because they are all thrown outward from some central origin point in ordinary space. This is exactly where people get stuck. Our everyday intuition wants a picture like a bomb going off in air, or shrapnel flying out from a center. But in cosmology, there is no outside space that the universe is expanding into, and no privileged point inside that expansion that you can mark as the center. The standard models of cosmology, the Friedmann-Robertson-Walker solutions of general relativity, describe a universe that is homogeneous and isotropic on large scales, meaning it looks roughly the same everywhere and in every direction. In that kind of universe, there is no unique point you can label as the middle. A common way to explain it is the raisin bread picture. As the dough rises, every raisin sees all the other raisins move away. No raisin sits at the special center of expansion, because the expansion happens everywhere at once. That's not just a cute image, that's actually a decent translation of the math into everyday language. The galaxies are the raisins, the dough is space-time itself. Sagittarius A star is simply sitting in one of those raisins, the Milky Way, and from its point of view, distant galaxies recede according to the same Hubble-Lemaitre law that any other galaxy would measure. There is nothing about its position that makes it central in a global sense. Now, connect this with the word orbit. An orbit is only a clean, useful concept in a bound system. Earth is gravitationally bound to the Sun. The Sun is bound to the Milky Way. The local group is gravitationally bound as a small island of galaxies. Inside those bound regions, gravity beats cosmic expansion. You can define a stable center of mass, and objects move around that center in more or less repeatable paths. That's where words like orbit and period and closed trajectory make sense. Outside those regions, space expands and structures drift apart, and there is no single mass in charge of everything. On scales where cosmic expansion dominates, gravity plus dark energy carve the universe into these bound islands, galaxies, groups, clusters, sometimes bigger associations, and those islands move away from each other over time. Between them, there is no overall center of rotation. The pattern is not like planets around a star, it's more like pieces of a flexible grid stretching. So the moment you cross from inside a bound system to between bound systems, the simple meaning of orbit fades out. That's why the question, what does the universe orbit, is empty. The observable universe doesn't orbit anything. It is the arena in which local orbits exist. The universe doesn't sit inside a bigger container circling some larger object. It's the total space-time geometry that everything, including Sagittarius A star, lives inside. So if you keep pushing the question, what does Sag A star orbit, up the ladder, galaxy center, local group barycenter, Laniakea flow, CMB frame, and finally ask, okay, beyond all that, what does it orbit as part of the entire universe? The honest answer is nothing. At that final level, there is no higher central mass for it to circle on a closed path. There is just motion inside an expanding space-time with no global center. This is the conceptual breaking point in the video. Up close, orbit feels like a universal rule. You grow up with the idea that everything orbits something bigger. Moons orbit planets, planets orbit stars, stars orbit the galactic center, galaxies orbit in clusters. It feels like an infinite chain, but it isn't. Orbits are a local behavior of gravity inside bound systems. On largest scales, the main thing is not orbits around a point, it's the geometry of space-time itself, its expansion and the distribution of mass and energy that curve it. So where does that leave Sagittarius A star? Locally, it absolutely sits at the heart of a tight orbital dance of stars, gas, and plasma. On galactic scales, it's one term in the Milky Way's center of mass. On group scales, it's just a passenger in the Milky Way as that galaxy moves in the local group. On supercluster scales, it falls as part of a flow in the cosmic web. And on the full universe scale, all of those motions are just particular examples of how matter moves in an expanding, almost uniform cosmos, with no special central seat for any black hole, no matter how massive. And that brings up an interesting comparison point. If Sagittarius A star is not special in this sense, what about the really huge black holes in other galaxies, the ones thousands of times more massive, sitting in galaxy clusters? Do they have more dramatic orbits, or are they just playing the same game, just with bigger numbers? Here's a detail that people often miss. Sagittarius A star feels huge to you only because you're comparing it to normal stars. In the family of supermassive black holes, it's nowhere near the top. It's more like a mid-sized member in a crowd of giants. Take the black hole in the galaxy M87. That one weighs in at roughly 6.5 billion solar masses. That's over 1,000 times the mass of Sag A's 4.3 million suns. If you line them up, Sag A would be the lightweight. So when you think our black hole at the center of the galaxy must be the ultimate anchor, remember there are black holes out there that dwarf it. The Event Horizon Telescope has even imaged both M87 and Sag A, and the size difference in their shadows matches that mass difference. Sag A is big enough to dominate the inner light year of the Milky Way, but on the list of cosmic extremes, it doesn't sit at the top. So does that mean the really big black holes have bigger orbits or more important orbits in some sense? Not really. The same rules apply, just scaled up. Put a supermassive black hole at the center of a galaxy that lives in a dense galaxy cluster, and that whole galaxy can move around in the cluster's gravitational potential. The central galaxy in a cluster, the brightest cluster galaxy, doesn't always sit perfectly still at the exact center of the cluster's dark matter halo. It can slosh around a bit, moving at a few hundred kilometers per second relative to the cluster's center of mass. Its central black hole comes along for the ride. So even a multi-billion solar mass black hole in a cluster core is not sitting at some ultimate universal center. It's orbiting, or more accurately, moving around, a bigger barycenter defined by all the galaxies and dark matter in that cluster. Now add galaxy mergers to the picture, because that's where things get really dynamic. When two galaxies merge, each usually brings in its own central black hole. After the stars and gas start to settle into a new, larger galaxy, the two supermassive black holes sink toward the middle due to dynamical friction, losing orbital energy as they plow through the surrounding matter. They form a binary, two black holes orbiting their common center of mass. That's a real orbit in the cleanest sense. They loop around each other, and as they do, they radiate gravitational waves, ripples in space-time. Those waves carry away energy and angular momentum, and the orbit shrinks. Eventually, the two black holes coalesce into a larger black hole. But the story doesn't stop there. The gravitational waves they emit are not always perfectly symmetric. If more momentum is carried away in one direction than another, the new black hole gets a recoil kick in the opposite direction. Simulations and some observations suggest these kicks can reach thousands of kilometers per second in extreme cases, though more often they're lower. Even a few hundred kilometers per second is enough to shove the merged black hole away from the center of its host galaxy, sometimes thousands of light years, before the galaxy's gravity slowly pulls it back or it settles into a new offset orbit. So the picture of a black hole as a fixed, eternal pin in the middle of a galaxy is wrong in general. They move, they merge, they recoil, they respond to the same gravitational environment as everything else, just with more inertia. So why does Sagittarius A star look relatively calm compared to these dramatic stories? The main reason is history. The Milky Way hasn't had a major head-on merger with another big galaxy of similar mass in the last billion years or so. We've been snacking on much smaller dwarf galaxies, not smashing into an equal partner. That means our central region has not been shaken up by a recent billion-to-billion black hole merger. Sag A hasn't received a huge gravitational wave recoil kick. Its motion around the Milky Way's barycenter is small and slow, dominated by the gentle tugs of the nuclear star cluster and the larger dark matter halo, not by some violent recent collision. So in context, Sagittarius A star is just one member of a very large family of supermassive black holes. Some live in quiet disk galaxies like ours. Some sit in massive ellipticals at the centers of clusters. Some are parts of binary systems on their way to merging. Some may be recoiling through their hosts after a collision. All of them are doing their own small-scale orbits and local gravitational potentials, and all of them are also being carried along by the larger motions of their galaxies, groups, and clusters. There is nothing cosmically unique about Sag A's orbit. It's interesting because it's close enough for us to study in detail, not because it occupies a special position in the universe's hierarchy. And this brings up a key point for you as the viewer. If these black holes can move, merge, get kicked, and still end up near the centers of their galaxies, then their orbits depend heavily on the timescale you look at. On one timescale, they're almost fixed. On another, they're doing tight loops. On another, they're drifting through a cluster. So the next thing you really need to see is how orbit periods range from minutes near a black hole's event horizon to years for nearby stars, to hundreds of millions of years for galactic motion, to billions of years for group and cluster flows. Right now, your whole picture of orbit is probably locked to one timescale, Earth going around the Sun in a year. But around Sagittarius A star, the story stretches from minutes to billions of years. And the scary part is, what you think the black hole orbits depends completely on how long you're willing to wait. Start right down near the event horizon. Close to the edge of Sagittarius A star, material can orbit in minutes. Not years, not days, minutes. The gravity is so extreme that gas and plasma in the inner accretion flow whip around at a significant fraction of the speed of light. When we see flares in infrared or X-rays from the galactic center, one way to model them is as hot spots of plasma, bright patches orbiting close to the black hole. They loop around on timescales of tens of minutes, maybe under an hour, depending on exactly how close they are and how the black hole is spinning. On those timescales, you don't care about the Milky Way or the local group or anything else. All that matters is the local gravity of Sagittarius A star itself. The orbit is just plasma versus black hole, nothing more. Step back a bit and slow down the clock. Instead of minutes, think in years. Stars like S2 orbit Sagittarius A star in about 16 years. That's short enough that human teams can watch full loops within a career. We literally have data of S2 going around the black hole, passing closest in, swinging out again, and repeating. At that distance, the speeds reach thousands of kilometers per second, and general relativity shows up plainly. We see gravitational redshift, where the star's light loses energy climbing out of the black hole's gravity. We see the orbit precess. The ellipse rotates slightly each time around, just like Mercury's orbit around the Sun, but much more dramatic. On decade timescales, what is orbiting what is simple. These stars are orbiting Sagittarius A star, and the black hole is effectively the fixed center. Now zoom way out and change the unit again. Think in hundreds of millions of years. The Sun's orbit around the Milky Way is about 230 million years per lap. That's the timescale where the black hole's mass becomes a tiny fraction of the total, and the dark matter halo plus all the inner stars take over. Dinosaurs appeared, evolved into a huge variety of species, and went extinct all within less than 2 of these galactic years. Modern humans have existed for something like 300,000 years. That's about 0.00113 of a single galactic orbit. So in terms of the Sun's 230 million year path, human history isn't even a footnote yet. On this timescale, the relevant orbit is the Sun around the Milky Way's center of mass. Sagittarius A star is part of that center, but only as one contributor to the total gravity. Stretch the clock again, now to billions of years. That's the scale of group dynamics, like the possible future interaction between the Milky Way and Andromeda. Whether those two big galaxies actually merge in about 5 billion years, or take closer to 10 billion years to fully combine, is still being refined with better data from Gaia and Hubble. But in either case, these are multi-billion year stories. The shape of the local group, which galaxies are closer, which ones have merged, which ones have been flung out, is a long, slow evolution. On this timescale, timescale, talking about Sagittarius A star individually is almost pointless. The important orbit is the Milky Way as a whole, moving with Andromeda and the rest of the local group around the local group barycenter, and then that whole package flowing as part of Laniakea. The black hole is now just a passenger glued into one galaxy in that bigger system. So put this all together. On our timescales, Sagittarius A star is the anchor, and bits of plasma orbit it near the event horizon. On decade timescales, nearby stars like S2 orbit the black hole, and we watch relativity in action. On 100 million year timescales, the sun's 225 kilometers per second motion around the Milky Way becomes the main orbit that matters to you. On billion year timescales, the Milky Way and Andromeda and the rest of the local group drift and collide and fall through the cosmic web. Change the time window, and the answer to what does it orbit changes with it. There is no single timeless answer, and this sets up the next critical step, because somewhere between plasma orbiting in minutes and galaxies drifting for billions of years, you cross a line where gravity can no longer win against the expansion of the universe. Inside that line, orbits make sense. Outside it, you just get flow. To really finish the story, you need to see where gravity stops making tight orbits and where cosmic expansion takes over, and what that boundary means for Sagittarius A star's maximum meaningful orbit. There's a hard limit to how far you can push the word orbit before it stops being honest, and that limit is set by the fight between gravity and cosmic expansion. This is the part almost nobody talks about when they say everything orbits something bigger. At some scale, that sentence just dies. The key idea is simple. There are bound scales and unbound scales. On small enough scales, gravity is strong enough to keep things held together forever, or at least for times much longer than the age of the universe. Planets are bound to stars, stars are bound to galaxies, galaxies in a small group can be bound to each other. Inside those regions, you can define a center of mass, and you can talk about orbits in a clean way. But beyond a certain distance, the expansion of the universe plus dark energy wins. Space stretches faster than gravity can pull things back in. Once you're out there, you don't really have orbits anymore. You have the Hubble flow, galaxies receding with speeds that grow with distance. For Sagittarius A star, and for you, the Milky Way is very safely on the bound side of that line. Our galaxy, its dark matter halo, and the immediate companions like the Large Magellanic Cloud and the other close dwarfs form a tightly bound unit. The gravitational pull inside the system easily beats the effect of cosmic expansion. Space can stretch all it wants. It does not rip our galaxy apart. The distances between stars inside the Milky Way are set by gravity, not by the overall growth of the universe. When you talk about the sun's 230 million year orbit around the galactic center, or stars like S2 looping around Sagittarius A star in 16 years, expansion is irrelevant. These motions are deep inside the zone where gravity dominates. The same is true, though a bit more delicately, for the entire local group. The Milky Way, Andromeda, and the handful of other dwarfs that are clearly bound to them form another island that will not be pulled apart by expansion. We know this because Andromeda isn't receding from us, it's heading toward us at 100 to 120 kilometers per second. Even though the Hubble flow at 2.5 million light-years would try to push it away, gravity between the two big dark matter halos cancels and overrides that outward push. On this scale, you can still talk about a barycenter, the local group's center of mass, and about the group members moving around that point in very long, very messy orbits. It's not a neat two-body problem, but it's still a bound system. Now, step up one more level to structures like Laniakea Supercluster. Laniakea is huge, about 500 million light-years across, and it contains multiple clusters and groups, including ours. But here, we're right on the edge of what bound really means. Parts of a supercluster can be gravitationally connected for a long time, but as dark energy continues to accelerate the expansion of the universe, the outer regions can start to slip away. Some clusters inside Laniakea may remain tight together. Others may slowly become isolated, and large stretches of the structure will eventually end up outside each other's effective reach. That's why the idea of a stable, closed orbit at supercluster scales is shaky. The mass distribution is not static, the expansion is speeding up, and the system is not guaranteed to stay bound as one unit. You don't have a single permanent center that every galaxy and every black hole will circle around forever. You have flows, infall, and in the long term, a kind of breakup where only smaller, denser pieces remain gravitationally self-contained. This gives you a very practical cutoff for the original question. You can define a maximum meaningful orbit for Sagittarius A star. It clearly orbits within the Milky Way's barycenter, pulled by the combined mass of stars, gas, and dark matter. It clearly participates in the local group dynamics because the whole Milky Way is moving in that group's gravitational field. Once you try to push beyond that to say Sag 8 orbits Laniakea or orbits the Great Attractor in the same sense, you're stretching the word orbit past its breaking point. Out there, over hundreds of millions of light years, what you really have is large-scale flow in an expanding universe, not closed, repeatable paths around the single mass. When someone asks, okay, but what does Sag A star orbit beyond the galaxy? What is the next bigger thing? They're not just asking for a bigger object. They are switching, without realizing it, from a bound system question to an unbound expansion question. It's like trying to use the rules of a small closed machine to describe a whole weather pattern. The language doesn't carry over. So the honest answer is there is a horizon to how far orbit makes sense. Inside that horizon, for Sagittarius A star, you have real orbits in the Milky Way and real participation in the local group's motion. Beyond that, you should stop looking for a larger central body and start thinking in terms of barycenters, flows, and space-time geometry. The question is no longer, what does it orbit? It's relative to which center of mass and on what scale are you even defining motion? And that brings you straight to one more layer of the story that you can't skip. We've already been using barycenters, centers of mass, without thinking about it, in the Earth-Moon system, in the solar system, and in the galaxy. To really wrap up what Sagittarius A star orbits, you need to make that idea explicit, from your backyard all the way out to superclusters, and then show why there is no final absolute barycenter for the entire universe. You've already been dealing with multiple centers your whole life, you just never had to name them. The universe has been sneaking barycenters into your everyday physics from the start. Take the Earth and the Moon. You probably say the Moon orbits Earth and move on. But technically, both of them orbit a shared center of mass, the barycenter. In the Earth-Moon system, that point lies inside Earth, but not at its geometric center. It's shifted toward the Moon by about 4,600 kilometers, roughly 2,900 miles. So Earth doesn't just sit still while the Moon goes around. Earth does a small wobble around that internal point. You don't notice because the wobble is tiny compared to Earth's size, but it's there, and it matters if you're doing precise navigation. Same thing with the whole solar system. We talk about planets orbiting the sun, but the real anchor is the solar system barycenter. Jupiter is so massive that it pulls hard enough to yank that barycenter outside the sun's surface at times. When that happens, the sun itself is literally orbiting a point in empty space just outside its own body, doing a small little loop while the planets do their own loops. It's not just planets orbiting a fixed sun, it's a whole family of bodies moving around a common center of mass. So you're already comfortable with this idea without thinking about it. You're used to the idea that the center of motion is not always located inside the biggest object, and not always at some obvious geometric middle. It's a calculated point, a balance point determined by how the mass is distributed. Now, scale that up and plug it straight into the Milky Way. When astronomers say the sun orbits the galactic center, they really mean the sun orbits the Milky Way's barycenter. That barycenter is defined by every mass in the system, hundreds of billions of stars, cold gas clouds, hot gas, dust, the dark matter halo, and yes, Sagittarius A star. The black hole is one term in the sum, a heavy one, but still just a term. If you could move enough mass around in the bulge or the halo, you could shift the galaxy's barycenter without changing the black hole at all. So center of the galaxy is not the location of Sag A star by definition. It's the center of mass of the Milky Way's total mass distribution. The fact that the black hole happens to sit very close to that point is the result of the galaxy's history and dynamics, not a built-in rule of the universe. In principle, if our galaxy had gone through different mergers or had a different dark matter profile, the exact barycenter could be offset more from Sag A. The black hole would then orbit that point in a clear and noticeable way, the same way the Sun orbits the solar system barycenter. The same logic climbs up another level in the local group. The local group barycenter is the balance point of the Milky Way, Andromeda, the Large Magellanic Cloud, and all the other dwarfs, weighted by their mass and positions. It sits somewhere in the space between the Milky Way and Andromeda, not inside either one. Because Andromeda is slightly more massive, and because the LMC and other satellites pull in their own directions, that barycenter is shifted toward them. Our entire galaxy, disk, bulge, dark matter halo, and Sagittarius A star, nailed in near the middle, is literally wobbling around that point, along with Andromeda and the rest. On that scale, the center is not a galaxy, it's a location in otherwise empty space, defined by the total mass pattern. So now you've got barycenters at 3 levels you can picture: Earth-Moon system, solar system, Milky Way, and then the local group. Each time, center is not some sacred physical object. It's a calculated balance point. That's the pattern you need burned into your brain before the last step. Because when you hit the universe as a whole, that pattern stops. General relativity doesn't give you a barycenter of all existence. The equations don't single out a special point in space-time as the universal pivot where everything balances. Instead, they talk about how matter and energy curve space-time everywhere, and how objects move along paths in that curved geometry. In a homogeneous expanding universe, there is no unique global center of mass. Every observer is allowed to treat themselves as at the center of their observable universe, and the large-scale laws look the same. That's why the question, what is the barycenter of the whole universe, doesn't have a physical answer. It's not like we haven't found it yet, it's that the theory doesn't define one. You can choose coordinates in lots of different ways. You can pick convenient reference frames like the CMB rest frame, but none of those are a true physical pivot point in the way the solar system barycenter is. Once you get to that level, the phrase, "what does it orbit?" stops being unique and frame independent. You can always pick a coordinate system that makes something look like it's orbiting something else, but that's just math convenience, not a deep physical statement. Sagittarius A star does not sit on a cosmic throne. It is just another mass in a universe where center is something you define for a given system, not something the universe hands you at the top level. Locally, it looks like the center of a furious storm of gas and stars. On bigger scales, it's just cargo inside the Milky Way, which is cargo inside the local group, which is part of a flow in Laniakea, all moving through an expanding space-time with no final pivot. And now you're finally ready for the clean, stacked answer you came for at the start, the actual hierarchy of what does Sagittarius A star orbit from the inner light year all the way out to the edge of what the question even means. So far you've seen the big picture, but here's the uncomfortable part. A lot of this is still a work in progress. We know the rough hierarchy of what pulls on what, but the exact details of Sagittarius A star's motion depend on numbers we're still tightening, especially the shape and mass of the Milky Way's dark matter halo and the exact motions of nearby galaxies. The story can sharpen, and in some extreme cases, it could even bend. Start with the halo, because that's the real heavyweight in the room. Right now, estimates for the Milky Way's total dark matter halo mass span roughly a factor of 2. Is it closer to 1 trillion solar masses, or 2, or somewhere in between? That difference matters. It changes how strongly the outer halo pulls on the disk, how hard the galaxy tugs on the Large Magellanic Cloud, and exactly where the true barycenter sits. To narrow this down, we're measuring the motions of as many tracers as possible: stars in the outer disk, halo stars high above the plane, globular clusters on long orbits, and tiny satellite galaxies. Their speeds and directions tell you how deep the gravitational well is at different radii. Then you fit a halo model to that. This is where machine learning is starting to show up. taking giant kinematic datasets and inferring which halo parameters best reproduce the overall motion patterns. The more we tighten those fits, the better we know the galaxy's center of mass, and the more precisely we can say what kind of orbit Sag A star has inside that potential. Then there's the clumpiness of the halo, the subhalos. Every time someone finds a new dark matter subhalo, usually through its effect on a stellar stream, we learn something about how smooth or lumpy our halo really is. You take a long, thin stream of stars, the debris of a dwarf galaxy that was ripped apart, and you look for gaps, kinks, or sharp density changes. Those features are like fingerprints of invisible masses that passed by and perturbed the stream. That tells you there was a clump there, maybe tens of millions of solar masses with almost no visible stars. Each detection adds another piece to the 3D map of dark matter around us. Over long times, a halo that is more lumpy can shift the galaxy's barycenter slightly as subhalos orbit and merge. The shifts are small, but if you want the cleanest possible answer to what does Sag A star orbit exactly, this structure matters. Now, zoom in on what Gaia is doing to our view of the local group. ESA's Gaia mission is measuring positions, distances, and velocities for over 1 billion stars in the Milky Way. That alone transforms our map of the galaxy's structure and mass. But Gaia also measures the proper motions, the tiny sideways motions on the sky of other galaxies in the local group, including Andromeda and many dwarf galaxies. Before Gaia and precise Hubble work, we knew Andromeda was coming toward us, but we were fuzzy on how much sideways motion it had. That sideways motion decides whether we're heading for a direct smash, a close flyby, or something in between. Better motions mean better models of the local group's barycenter and the path of the Milky Way around it. For Sagittarius A star, that translates into a more precise velocity and trajectory on group scales, instead of just it kind of falls toward Andromeda and larger structures. Next, go all the way back to the black hole itself. Right now, we track Sagittarius A star's position with very long baseline radio interferometry, and we model stellar orbits like S2 with high-precision infrared observations. Future upgrades make that sharper. More sensitive radio arrays with longer baselines can pin down the black hole's proper motion to even smaller fractions of a milli-arcsecond per year. Better infrared instruments and GR-level orbit fits can detect tiny deviations in stellar paths caused by the combined pull of the black hole, the nuclear star cluster, and possibly intermediate mass black holes or dense dark matter near the center. Put together, this turns the inner few parsecs into a kind of slow-motion N-body simulation we can watch in real time. Every extra decade of data shrinks the error bars on how much Sag A star wobbles, how offset it is from the exact inner barycenter, and how the mass inside that region is distributed. And then there's the possibility, however small, that some piece of the fundamental physics is wrong. Most of what you've heard in this script assumes standard general relativity plus dark matter. That framework fits an enormous amount of data, from stellar orbits to galaxy rotation curves to lensing maps and the cosmic microwave background. But there are alternative ideas. Modified gravity models like Mond-type theories and their more complex cousins try to explain flat rotation curves without dark matter by changing how gravity behaves at very low accelerations. Other exotic models suggest the black hole in the center might be some kind of dense dark matter core, or a different compact object instead of a classic event horizon black hole. Right now, observations like the event horizon image, the orbits and relativistic redshifts of the S stars, and the way mass is distributed on many scales all strongly favor the standard supermassive black hole inside a dark matter halo. To overturn that, you would need a new theory that matches all the existing evidence at least as well and makes new predictions we can test. So, could our picture of what Sag A star orbit be overturned? The basic hierarchy is very hard to shake. You would need a completely new understanding of gravity or dark matter that removes the halo, rewrites the local group dynamics, and changes how galaxies assemble without breaking everything else we've measured. Much more likely is that we refine the details. We'll get a sharper value for the Milky Way's total mass and shape, tighter constraints on how clumpy the halo is, better measurements of the LMC's pull on us, and cleaner tracks of Sagittarius A star's tiny wobble inside the central cluster. The skeleton of the story stays the same, but the exact numbers, the exact orbit shapes, and the exact barycenter positions get cleaner. And that leads perfectly into the final step. You now have all the pieces, from plasma loops in minutes to stellar orbits in years, to solar and galactic orbits in hundreds of millions of years, to local group flows and supercluster motion, and the role of dark matter and barycenters at every level. The only thing left is to stack it all together and give a straight, one-sentence answer to the question you started with, followed by the full layered version that shows just how far down the rabbit hole what does Sag A star orbit really goes. So, after all of that, what does Sag A star actually orbit? What is the honest, cleaned-up answer once you strip away the memes and the shortcuts? Let's just stack the levels, one by one, and see where the chain really stops. Start at the tightest scale, the local one. Inside roughly the inner light year around Sag A star, the black hole is the boss. Its gravity dominates everything there. Stars like S2 and S29, clumps of gas, hot plasma in the accretion flow, all of that is orbiting the black hole itself. Some of that plasma is looping around in minutes, those S-stars are looping in years to decades. On that scale, the question what does Sag A star orbit is backwards. Here, Sag A star is the central mass, and everything nearby is obeying its gravity. Now step up to the whole central region and the disk, the galactic scale. Once you move out to where the sun lives, about 26,000 light-years from the center, the picture flips. The black hole's gravity is still there, but it's tiny compared to the combined pull of the bulge, the disk, and the dark matter halo. All of that mass together defines the Milky Way's barycenter, its true center of mass. Sagittarius A star, the nuclear star cluster, the bulge, and the disk are all moving in that shared gravitational potential. So on this level, the accurate sentence is Sagittarius A star orbits the Milky Way's true center of mass inside a halo that weighs around 1 trillion suns. It is not the whole center, it is one part of the center. Now go one level higher, the group scale. Here, you stop treating the Milky Way as empty space with some galaxies around it, and you treat the whole Milky Way plus halo plus Sagittarius A star as one object. Alongside it, you have Andromeda, the large Magellanic Cloud, and the swarm of dwarf galaxies. Put all that mass together and you get the local group barycenter, a point in space between the Milky Way and Andromeda, shifted by the LMC and other dwarfs. That's the balance point of the group. Both big galaxies with their central black holes welded in orbit or slosh around that point over billions of years. So on this scale, it makes no sense to pull Sag A star out by itself. The whole Milky Way system is what's orbiting, and Sag A star is along for the ride. Next up is the supercluster scale. The local group doesn't sit in a vacuum. It sits inside the flow of galaxies we call Laniakea, about 500 million light-years across, where many groups and clusters stream toward the same deeper gravitational basins, including the Virgo cluster and the region we call the Great Attractor. Here, the motion is not a neat ellipse around a single center. It's more like a one-way fall down a complicated gravitational landscape, set by the full pattern of mass and by the expansion of the universe. The local group, with the Milky Way and Sag A star in it, is part of that bulk flow. So on this level, you don't say Sag A star orbits Laniakea. You say Sag A star is inside a galaxy that flows with the local group along the filaments of the cosmic web toward regions of higher density. Finally, go to the biggest scale we can talk about meaningfully, the cosmic scale. Now you use the cosmic microwave background as your reference frame. In that frame, the sun is moving at about 370 kilometers per second, and the local group is moving at around 600 kilometers per second. Sagittarius A star shares essentially the same bulk velocity because it's glued into the Milky Way's core. On this scale, there is no central object it's orbiting. There is no center of the universe for it to circle. There is just motion through expanding spacetime, with speeds and directions set by all the gravity acting on us, stacked over billions of years. If you want one clean, quotable line, here it is, straight. Sagittarius A star orbits the Milky Way's true center of mass, which orbits the local group's center of mass, which falls through a cosmic web that has no single center at all. That's the short version. But the real punch comes when you flip the question back on the viewer. You started with a simple idea. Everything in the galaxy orbits the black hole at the center. Now you can see that's only true in a tiny inner region. For you, personally, on human timescales, the orbit that matters is Earth around the Sun, 1 year, 150 million kilometers out, about 93 million miles. On slightly larger scales, the important orbit is the Sun around the Milky Way's barycenter, 230 million years per lap, set by hundreds of billions of suns and the huge dark matter halo. On local group scales and beyond, you stop having closed orbits at all. You just have motion through an expanding universe, measured against the CMB with no ultimate rest frame and no throne for any object, even a supermassive black hole. So the final twist is this. The idea of orbit that feels so fundamental to you is actually local. It works beautifully inside bound systems where one mass or one center of mass dominates. But as you climb the ladder of scale, that idea slowly breaks. First, it turns into motion around the barycenter defined by many masses. Then it turns into long, messy interactions of whole galaxy groups. And then it turns into large-scale flow in the cosmic web, where geometry and expansion matter more than neat loops. Asking what does Sag A star orbit on those top levels is not a deep question anymore. It's just the wrong tool. So where does that leave you? You are not circling some ultimate cosmic king with a final immovable center at the top of the hierarchy. You are riding a chain of motions nested inside motions. Earth around the Sun around the Milky Way's barycenter, the Milky Way around the local group barycenter, the local group streaming inside Laniakea, all of it moving through expanding space-time at hundreds of kilometers per second, anchored to nothing except the laws of physics that decide how mass and energy bend space-time and how things move in that bend. And once you see it that way, the question quietly changes. It's no longer, what does Sag A star orbit? It's, on what scale are you looking and which center of mass are you choosing to care about today? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.